said, we assume there's some kind of set of basis functions that allow us to express square integrable functions, f and g. And in practice, so there are many different kinds of bases you can extract and define, but probably the simplest is what's called the eigenfunctions of the Laplace-Beltrami operator. And these are defined as solutions to this eigenvalue problem where you have some operator delta that acts on a function, and we're looking for functions such that delta fi equals lambda I fi, where lambda I is a scalar. And this Laplace-Beltrami operator is basically an extension or a generalization of just a standard Laplacian from the Euclidean domain, so the sum of the square, or the sum of the second partial derivatives, and it can also be defined as minus the divergence of the gradient. And if you're not familiar with this, you can just think of this as basically just a very natural generalization to Fourier bases or Fourier series to surfaces. And just like Fourier bases, these eigenfunctions of the Laplace-Beltrami operator, they are ordered, so they have a notion of scale. So you can think of it as kind of frequencies, right? So, Fourier basis is ordered from low frequencies to high frequencies. And the same is true for these Laplace-Beltrami eigenfunctions. So there's a kind of a notion of scale. So, for example, the first eigenvalue, the smallest eigenvalue, lambda 0, is always 0, so it's a constant, and it corresponds to a constant function, so this is kind of the smoothest function. And then lambda 1 is the first non-zero eigenvalue, corresponds to basically a function which is as smooth as possible while not being constant. So this is kind of the lowest frequency function you can define that is not constant. And then it kind of continues like that. So there's a natural notion of multiscale when you consider these eigenfunctions. And what's nice is that basically, these eigenfunctions, they form an orthonormal basis for the space of all square integrable functions. So any function that is square integrable can be written as a linear combination of these eigenfunctions of the Laplace-Beltrami operator. And also, what's important for us is that they can be computed efficiently in practice. So, for example, there's you can use a discrete sparse matrix eigensolver to compute these lambda i's and phi i's. And if you're interested, there's some basic code on our course website where you can play with it and try it out. Now, okay, so this is what we use. So remember, basically our observation was that this T sub f was linear, and so we have this linear transformation between the coefficients of different functions. And this linear transformation is exactly what we'll call a functional map. So basically, we have some underlying functional transformation. So it takes functions on one shape to functions on the other shape, and we can express it as basically a change of basis matrix, where you have some basis which is the eigenfunctions of the Laplace-Beltrami operator on one shape, and you have another basis on the target shape, and this matrix is just a change of basis matrix that allows you to take a function expressed in one basis and produce the corresponding function expressed in the other basis, right? And so this matrix C is exactly what is called a functional map. And so I like this image that maybe is a bit more intuitive and it kind of summarizes everything that I've said before. So suppose we have these two shapes, M and N, so this cat and dog shapes. Now, if I have some function f, like this sort of indicator function localized on one of the paws of the cat, I can first decompose it as a set of coefficients ai with respect to some basis. And the important thing to note is that this basis doesn't depend on f. It's pre-computed as some kind of universal basis. So I have a set of coefficients. And now, in order to transfer this function on this shape n, and I get some new function g, or I can I can express this function f in the basis, so this is the pseudo-inverse operation here, and then I can apply a change of basis transformation, and then I can reconstruct this function with respect to the basis on the target shape. And so this functional map is kind of a translation matrix that allows you to take the coefficients ai and translate them into coefficients bj, right? And if you want to transfer a function using that, you can just apply this little change of basis expression. So this is nice, and it kind of allows us to encode correspondences. So if I have, for example, this source shape and different correspondences, like this one encodes a mapping between the source and target that is kind of what you would expect, like the left paw goes to the left paw, the left ear goes to the left ear. And this mapping has a nice compact representation of the functional map. And another correspondence is basically the same, except for mapping left to right. So this is still has this nice sort of diagonal structure, which kind of we can observe empirically, but also there's an underlying sort of geometric reason, which I'll describe in a second. And the other thing is, like, if you take a mapping, for example, you map the tail of the cat to its head, then you end up with some functional map that looks like this. It doesn't have this nice structure. It looks kind of noisy. So, if you're interested, you can try this out on the course website as well. Okay, so what's nice is that, we can either use the full basis, so we can take all of the basis functions, or we can use a truncated basis, so only use the first, k smoothest functions, the functions corresponding to the lowest frequencies. And if you do that, then you can take a map. So let's say I have this map between the source shape and different kind of target shapes of these different kinds of cats, and they have about 20 vertices each. Then if you look at the error that you're making, so here on the x-axis I plot the number of basis functions that we use, and on the y-axis I'm plotting the error, the reconstruction error that I'm making for the map, for the point-to-point map. And basically below about 80 eigenfunctions, the error that you're making is less than one edge length of the mesh. So what that means is that, I have these shapes with 28,000 vertices each. I can encode good correspondences between them using matrices of size 80 by 80. And this is typically the kind of size that we use in practice. Now, right, so now what's nice is, so there's this kind of, at first seems very simple, but it turns out to be extremely useful. And there are many properties of this functional map matrices that you can exploit, and this is what we've been doing for the past few years. Basically, one thing you can show is that map composition. So if I have three shapes and maps between them, and if I want to compose maps, then I can just do this by matrix multiplication. If I want to find a map inverse, I can do this through matrix inverse, and in some cases actually transpose, for some reasons I'll describe. And then other things you can do, like, for example, take averages of maps. If I have two correspondences, like I have these two shapes, and I have one map that is maps right to left, and the other one maps left to right, I can take some kind of a convex combination of these. So taking averages of pointwise maps doesn't make too much sense, because how do I take an average between two images of points? But taking averages of functional maps makes a lot of sense. So that's this is something that we can use in practice. Okay, so this is the essential properties, and I wanted to describe briefly a basic pipeline for computing correspondences using this representation. So everything that I've said so far was based on this idea that we start with some mapping, some correspondence T, and we convert it to this functional map, and we use some of its properties. But of course, in practice, this doesn't help us because we start with just a pair of shapes, and what we'd like is to find this correspondence. And so we need to find a way to do this extraction, a computational functional map, without having the pointwise map first. So the question is, given a pair of shapes, and how do I use this representation to actually find the correspondence? And maybe a higher level question is, okay, we just somehow changed the point of view. We haven't actually introduced any new information into the system. Does this functional representation actually help us to compute these maps in practice? And, the answer, of course, is yes. Otherwise, I wouldn't be talking about it. But how exactly we do this, I think, is maybe somewhat informative. So first of all, there's a very basic observation that you can make, which is the following. That suppose that we don't know the transformation, so we don't know this mapping C, right? So we don't know what the functional map is, but sometimes we can compute certain properties that we expect this C to preserve. So for example, if a map preserves distances, then it should also preserve curvature, like Gaussian curvature. And so what we can do is we can compute, some functions, some curvature function on one shape, express it as in the basis of the shape, and then we can compute the corresponding curvature on the second shape and express it in that basis. And now we say, okay, we don't know what the C is, but we know that C times this coefficient matrix, coefficient vector A should be equal approximately to the coefficient vector B, right, which we can pre-compute. And once you do that, it's very easy to see that if you have enough such pairs of functions, you can recover C just by solving a linear square, least squares system. And this kind of constraint is actually quite general. So, for example, if you have some attribute defined in the shape, like color or texture, you can convert it into this function preservation constraint. Also, if you have some descriptors, so there are different kinds of descriptors that have been proposed in the past, and you can typically convert them into this form that basically expresses them as functions on surfaces. Also, in case you do have some landmarks, you can, like landmark correspondences between certain points, you can convert them into functional correspondences just by basically, for example, computing the distance to the landmarks, and that becomes a function preservation constraint. Or if you have some parts that you know should correspond, again, you can construct, for example, indicator functions. So this is very powerful and generic constraint. Another very constraint that's very useful is what we call commutativity with other operators. And what that means is that suppose I have a function defined on one shape, there's some operator that I can take, let's call it S of m, that takes this function and produces another function on the same surface. So for example, the Laplacian is this kind of operator that takes functions to other functions. And then I can define the following diagram. I say, okay, I first compute S of m and then map it through C. Should be the same as mapping it through C first and then applying S of n. And this can be written in this convenient form. And this energy, so if you're solving for C, this energy is quadratic in C, so this is very easy to optimize. What we can show is that if you have a functional map that comes from a point-to-point map, then there are many properties of point-to-point maps that you can read off, or you can kind of explain in terms of these functional maps. So the first one is, for example, remember I said that we're interested in maps that preserve geodesic distances. And there's a lemma or a theorem that you can show that basically a mapping, a point-to-point map, preserves geodesic distances if and only if the corresponding functional map commutes with the Laplace-Beltrami operator. So this commutativity that we just wrote down actually corresponds to preservation of distances. And in what this means is actually this implies that isometries lead to diagonal or block diagonal functional maps. So what we observed in this maps between cats is actually very general behavior that like diagonal functional maps are good, and it comes from this lemma. So this is the kind of pipeline that we proposed for finding functional maps based on all of these observations. So we are given a pair of shapes m and n. So first we compute a small set of basis functions, like the eigenfunctions of the Laplace-Beltrami operators. We store them in matrices phi m and phi n, where columns are individual functions, so each column is one function. Then we compute some descriptor functions, like, for example, heat kernel signature, wave kernel signature, and we express each of these as coefficients in this pre-computed basis, and we can store the corresponding coefficients in matrices A and B. So here I use bold notation. A and B basically means these are coefficients with respect to some basis, but they're still matrices. And then we find the optimal functional map by basically solving for the C that minimizes a sum of two terms. The first term basically says, okay, I want to find a mapping C that preserves the descriptor. So for every column A, after I apply C to it, I should get the corresponding column B. It should be, this is what is called descriptor preservation. And also the C should commute with the Laplacian operator, right? And in practice, the Laplace-Beltrami operator, when expressed in the basis of the Laplacian, is actually a diagonal matrix of eigenvalues. So this is a very easy constraint to enforce. And what's important is that this energy that we defined has two very nice properties. The first one is that the number of unknowns is only k by k, so this is this matrix C, and it doesn't depend on the number of points on m and n, right? So for example, if I have 100 by 100 functional map, I have 10,000 unknowns, but the number of points on the surface can be arbitrarily high. And the other nice thing is that this is this is a convex problem. It's actually a least squares energy. So we basically transformed something that was highly nonlinear, highly non-convex into a convex problem that is easy to solve in practice. And finally, we convert this functional map to a point-to-point map if we need to. So in some cases, you might be okay, you might kind of get away with just keeping the functional map. But if you need to convert it, then we basically follow the procedure that I described in the beginning. So there is so this is a kind of high-level pipeline that we just described in 2012. There's a variant of this pipeline that we introduced last year at SIGGRAPH Asia, so 2018. And if you're interested, this is kind of I would say, more advanced version, and it has different kinds of different kinds of regularizations that we have found over the years to be very useful, and also optimization both in the spatial and the spectral domains. And so if you're interested, I basically recommend trying this code just to see how, if it maybe is useful in your setting, because it's kind of the advanced version of this pipeline. But just to give examples, basically these are the kind of correspondences that we can compute very fully automatically without any landmarks that are given. So these are the kind of point-to-point maps that we can get. And in this domain, we also use basically quantitative evaluation and comparison of different techniques. And the way that it works is that we have a bunch of shapes and a benchmark, and we create these kinds of plots where we, on the x-axis, we have some geodesic error. So basically for every point on each source shape, we know it's ground truth on the target shape. And for each method, we look, okay, how far is the point that this method predicts from the ground truth? And so this is what's called the geodesic error. And on the y-axis, we plot the percentage of correspondences that is below this geodesic error. So ideally, we want all correspondences to be at exactly 0 because they're basically exactly at the ground truth. But of course, that doesn't happen in practice. So, we plot different kinds of techniques. And this is the result that we showed in 2012. But since then, there's a lot of improvement. So, this is the kind of error that we're typically making. So the radius of 0.2025 is in blue, and, basically around 80 to 90% correspondences, I mean, these days it's closer to 100, are within this radius. All right. One important thing I wanted to highlight is that in some cases, you don't actually necessarily need to convert to a point-to-point map. So if you want to transfer a function, for example, if you want to find corresponding segment or label on a shape, if you're given a functional map, you actually don't need to convert it to a point-to-point one. And if you want to transfer segmentations, for example, in what we showed is that you can just construct indicator functions, see how they get mapped, and then this gives you a transfer of the segmentation without using the point-to-point correspondence. So this is kind of the basic pipeline that we have, and there are many different extensions to this pipeline. And I wanted to first give it as an overview because it's really the foundation of a lot of the things that we have done. So in the second part of my talk, I wanted to describe some of the recent extensions and improvements that we have made. Basically, I'll talk about two papers in a little bit more detail and mention some more at the end. So the first one is how to incorporate learning into this pipeline. And the second one is a recent method that we propose that will appear at SIGGRAPH Asia on very efficient, basically, refinement within this framework. So, this is still not published work, and it hasn't been presented, so you guys are some of the first to see it being presented. So the question of the first work is the following. So the pipeline that I described works fairly well if the initial descriptor correspondences are good. So what that means is that in practice, we often need to kind of curate the descriptors that we use to the particular kind of shapes or the particular kind of data that we have. And this is a bit of work, and in some cases the descriptors can be bad. So these are, for example, examples of commonly used shot descriptors. And as you can see, I mean, they kind of have some signal, but they're not very consistent with respect to the underlying correspondence. So of course, if that is the case, this pipeline that I described won't work very well. And so one question is, what can you do in this case? So there was a paper that was presented at ICCV 2017 that was called FMNet, and it basically tried to address this problem with supervised learning. And the idea is, say I have these pair of shapes, I can define some kind of a neural network, so that takes descriptors on this shape and also takes descriptors on the other shape. And basically, the weights of this neural network is fixed, so it's a single neural network. So it takes descriptors on the first shape and does something to them and creates basically new descriptors, and the same on the second shape. So it basically processes the descriptors, and then instead of using the original descriptors to compute the functional map, it uses these processed descriptors and passes them through what's called a functional map layer. And then it basically allows you to compute the correspondence, right? So this functional map layer is not learnable, it's a fixed layer. And then from this correspondence, you get a correspondence between the shapes. And so what is this network? The network that they defined is basically, it's a Siamese network. So basically you have these shared weights. So here the X and Y are the descriptors on the two shapes. So I have, from X, I compute some descriptor like shot, and then I pass it through a set of fully connected layers. And this gives me a new set of descriptors, right? These are called, so basically some new descriptors, and then I compute, so these are called F and G, and then I compute their coefficients with respect to the fixed basis, like the Laplace-Beltrami basis, and then I solve for the optimal functional map, and then if I want to find, basically, to compute a loss, I penalize how far this functional map is from some ground truth. And how do they do that? In their case, they basically converted this functional map to some soft correspondence by taking the small functional map and creating a large matrix of basically probabilities of how different points are connected, and then imposing a penalty that is the geodesic distance between the ground truth correspondence and the target point. And so this is basically a network. I mean, it has some nice properties in the sense that the descriptors are learnable, but it also has two limitations. The first limitation is, you need to have these ground truth maps if you want to solve this problem, basically if you want to learn the descriptors. And one question is, can we kind of get rid of these supervised correspondences? And the second is that it uses geodesic distances and basically these soft correspondences, so the soft map here. And these matrices are very large, and computing geodesic distances requires basically computing a matrix of size n by n, where n is the number of points that is dense, and is the distances between all pairs of points. So this is very expensive. So one question we wanted to ask is, can you perform all of these computations in the spectral domain? So the related question is, how do we kind of measure the quality of the map without using ground truth? And so there's actually, just to mention, a related paper in CVPR 2019 that does something similar, except they still use the geodesic distances, so it's not exactly the same is what I'm going to say. So what we propose is basically a variant of this idea where, again, we have a pair of shapes, 1 and 2. We have some descriptors, D1 and D2. We take these descriptors, we pass them through the same network, right, that is trainable, so we learn the weights of this network. And then this gives us the transformed descriptors. So T, in this case, is the transformation of the input descriptors. And now, instead of computing the functional map using the initial descriptors, we compute it using the transformed descriptors. So what we do is we basically compute two maps, one from shape 1 to shape 2, so this is C12, and another from shape 2 to shape 1, the C21. And these are just the standard, they're computed using the basic functional map estimation just by looking at the difference between the descriptors, the transformed descriptors. Once we have these two functional maps, we impose some penalty on them. So this is what we call E-reg. So this is the regularization penalty on this pair of maps. And this penalty is differentiable. So then we basically backpropagate this loss back to the computed descriptors and then backpropagate to the weights of the network. So I mean, this is kind of very simple pipeline. The whole maybe trick or the whole difficulty lies in this step. Like, what do we consider as the penalty for the functional map? So in our case, we basically use a penalty that consists of 4 different terms. The first is the bijectivity. So what's important here is that we use the 2 maps in 2 directions at the same time. And this actually helps a lot because it allows us to see how consistent these 2 maps are. So we impose a loss that is a weighted combination of different losses. And the first term is what we call bijectivity, which is basically how, when you compose these 2 maps, how far is the composition from identity. So this is like this cycle consistency loss that I guess is very popular in computer vision. And this is basically the same thing. The second one is we basically promote orthonormal matrices. So this is another loss that we impose on C. So orthonormal matrices correspond to basically area preserving maps. Then we also have this commutativity with Laplacian. And finally, there's another term that more or less, so I won't go into too much detail, but it basically promotes functional maps that arise from point to point 1. And these losses, none of them, so they're all fully in the spectral domain. So if a functional map is a size, 80 by 80, all of these matrices are 80 by 80. We never have to compute anything that's large, dense matrix. And so they're all expressed in this reduced basis. And what this means is that basically the final optimization is about 50 times faster than the FMNet learning procedure. And so we evaluated this on a range of data sets, and some of the data sets we released as part of a previous paper, and it's important because these data sets actually are remeshed. So we have some ground truth correspondence, but it's not one-to-one. So these are actually quite difficult quite difficult data sets. And we have different evaluations. So we either optimize on the entire set, or we take a subset for training and another for testing. Here it's a bit tricky to actually call it training because this is an unsupervised method. So there's no learning in some sense. But still, just to be fair to other techniques, we split the data set into training and testing just to see how well the method generalizes. So this very simple procedure, even though there are all these complex regularization and so on, it actually achieves state-of-the-art, at least at the moment, among unsupervised methods on these data sets. And we compare it to many different techniques, including the SIGGRAPH Asia paper that I mentioned. And even though it's very, very fast, it produces basically superior results. So this is just some comparison of the kind of results that you expect. So in this case, I'm showing texture transfer. So I have some source shape, and this is some texture painted on the source, and then I transfer this texture either the ground truth correspondence or using different methods. So we call this method SURFMNet, and so you can see that basically this texture is transferred very, very close to what the ground truth transfer does, and other existing methods. They actually do a reasonable job. I mean, it's not so bad, but there's still quite a bit of inconsistency. So this area has really advanced a lot in the past few years. So now techniques perform fairly well, but there's still some room for improvement. We also compared to unsupervised methods to supervised methods. And the difference here is that we used a subset of shapes for training and the other subset for testing. And this is a more difficult setting because even though our method is unsupervised, it still has to generalize to completely unseen data. But even in this setting, we basically produce results that I would say are comparable. I mean, in most cases, they're actually better, but you have to be a bit careful how you measure better in this case because we don't have the same amount of information. But just to be safe, we basically say that they're comparable to supervised techniques. So this I found really remarkable because supervised methods, they require some ground truth correspondences, and somehow they use those ground truth mappings. But this method is purely unsupervised and still can produce comparable results to supervised techniques. So I think just the fact that you have a lot of training data doesn't necessarily mean that your method is going to be better because how you use this training data is very, very important. So to me, this is kind of an interesting consequence. So this is some example of texture transfer and comparing to different supervised methods. So what we basically wanted to show is that FMNet, which is very similar architecture, performs significantly worse and is also slower. Okay, so this is oh, right. So just to illustrate what happens, so these are descriptors that we saw before the optimization. These are the short descriptors, and then after the optimization, the kinds of descriptors that you see is something like this. So what's interesting, I think, is that this method never has seen the ground truth correspondence, but somehow learned that the descriptor should be approximately like this, so they should be consistent with respect to this correspondence through all of these different penalties that we impose. So I think that's quite interesting. So this is a work that will appear in a couple of months at ICCB. And then the last thing that I wanted to describe very briefly in the next few minutes is another work that we are going to present at SIGGRAPH Asia. And it started by basically asking the following questions. So in the pipeline that I described, including in this learning-based method, we always have this choice of scale. So we start with some fixed number of basis functions, like we use, for example, 80 or 100 basis functions. And then we do this optimization in that scale. Now, one question is, can we do this progressively, right? Can we somehow maybe build up the scales, like the dimensionality progressively? And the other question is, if you think of the Laplace-Beltrami eigenfunctions as the generalization of the Fourier basis, then using like 100 basis functions essentially means you can only transfer low-frequency functions, so like the lowest 100 frequencies. But the general question is, if I give you this map that's encoded, let's say, 20 by 20, a functional map, can I still transfer higher frequency functions? And the related question is, can we speed up functional map refinement? So what we propose in this paper is essentially an algorithm that is probably the simplest algorithm I've ever published in any paper. And it's literally just 2 lines of code if you implement it in MATLAB. And it goes like this. So I suppose that I start with some functional map C1 and it's of size k by k. Okay, so this k can be quite low. Like, for example, in this example, it's 4 by 4. So it's really tiny, tiny functional map. Then we convert it to a point-to-point map T. And then in the next, so to convert it to a point-to-point map, we just use the same conversion step. And then to convert it to a functional map, we just increase the size of the basis by 1. So instead of using k by k, we use k plus 1 by k plus 1. And then we repeat this procedure for progressively larger k. And so this is it. Like, this is really the whole algorithm. And what is really remarkable is that even if you start with very poor maps, so here I have a 4 by 4 functional map between 2 shapes, there are like thousands of points, and the initial point-wise correspondence, if I transfer the colors, for example, from this shape to this shape, it looks like this. And it's very, as you can see, hopefully, it's quite noisy and discontinuous. And as we progressively do this, the map becomes smoother and smoother and more kind of expressive. And finally, we have a very continuous, very nice correspondence. So in some sense, this was to us a bit of a mystery for why this happens. So I'll first show some examples, and then I'll give a reason for why this has a chance of working. So just to show another example, so here's a pair of shapes. We took a set of descriptors. They're not super carefully, selected. We just selected some basic descriptors and constraints that were proposed in previous works, and we constructed a 50 by 50 functional map and converted it to a point-to-point map. It looks like this. So you see, it's kind of okay, but there are some problems. And then exactly using the same descriptors, we converted to a smaller functional map, in this case 20 by 20, and then ran this upsampling, what we call zoom out, to a larger size, 50 by 50. And then, even though we use the same descriptors, the quality of the map is much, much better. So here's a really extreme case that we used in our teaser. So we start between basically a pair of shapes. So this is a data set that I got from from a natural history museum here in Paris. There are people in the domain called comparative anthropology, and what they do is essentially they study bones of different species. And so, for example, they have CT scans of bones of different wild boars, and they want to find relations between them, so how similar or how different they are. So these are like these are raw data from CT scans, and it has topological noise. These are quite different shapes from different species. And so in this case, we start with a functional map, which is just a 2x2 matrix. It's really tiny. And then we run this procedure. And so the initial correspondence that you see is basically looks like this, and it's super noisy. And then we run this procedure, and then the final correspondence that we get looks like this. And it's very, it produces very nice, very smooth texture transfer. So here's, so I said that we call this method zoom out, and here's maybe one reason you can see why. So this is kind of what the intermediate functional maps look like as we do this procedure. So we start from 5x5 to 50x50. So you see it's a bit like a zoom out. You kind of have a higher and higher view of this functional map. And these images show the transfer of some high frequency function over time. So in the beginning it's noisy, and then it becomes much better. Here's another example where instead of increasing the size, we fixed the size of the large functional map, but we only plot the corresponding functional maps in the intermediate ones in the corresponding upper left corner, and